Colligative properties are those that depend only on the number of particles dissolved in solution and not the identity of the particles. And so let's look at what we can observe for water when we dissolve anything in water. And so we'll start by looking at this pressure temperature phase diagram of water and seeing what's observed. So the phase diagram after we dissolve some solute into water actually shifts. And so what we see is we see a shift something like this, where all the equilibrium lines are shifted a little bit here. And so let's look at what the consequences of these are. First, let's start by looking approximately at 1 atmosphere in this sketch. So we've got 1 atmosphere. If we were to look across at 1 atmosphere, we can find our normal boiling and normal freezing points in our sketch here. So here we've got our normal melting or freezing point. Right, so this will be 0 degrees C, and here's our normal boiling point, so the point at which the vapor pressure equals the atmospheric pressure, 100 degrees Celsius. Now if we look after we've shifted our phase diagram here by dissolving some solute in water, we can see that there's been a shift of the melting and freezing point to something lower, right? So we call this freezing point depression. And we see a lowering of the freezing point that depends just on the concentration and not the identity of the particle. And then we can see some other things. Look, our boiling point here has shifted up to some higher temperature. So we call this boiling point elevation. And then we also often talk about the colligative property, which is the vapor pressure lowering. So if we look here, we'll see that the vapor pressure line described by the Clausius-Clapeyron equation has shifted down. So this whole line has shifted down. Right? So this is vapor pressure lowering, which is intimately linked to the boiling point elevation. If the vapor pressure is lower, then we're going to have an increased boiling point. There's another colligative property known as osmotic pressure, but it doesn't fit nicely onto our phase diagram here. But let's focus just on the boiling point elevation and the freezing point depression for a moment. We're not going to be quantitative about this in this particular segment. We can be very quantitative about it, but we're going to talk more about the entropic reason for these. Alright, so let's make a graph here where we're going to plot the entropy on our y-axis, and we'll look at the various states of our pure liquid, our pure water, compared to these solutions. So here I'm going to draw in my pure liquid. Right, so it has some entropy associated with it, and so this will be my liquid water. I'll just label that L for liquid. And if I were going to then freeze the liquid to the solid state, then I'd expect that would have a lower entropy. And if I were going to then boil it to get it up into the gas phase, I'd expect that to have some entropy here. So this will be my gas phase entropy. So this is for my pure liquid. Now let's say instead I have a solution. So I have something dissolved in that solvent. So now I have to look at this, and now that I have something dissolved, the entropy of my solution should be higher than the entropy for my pure liquid, since I've got a composition, a mixture of two different particulate things. So we have the water and whatever is dissolved inside that solution. So this will be my solution rather than my pure liquid. So I'll just label that aqueous just to represent this is my solution. So I have the pure liquid and I have the solution here, which is water plus my solute. Now if I wanted to compare this to the gas and solid, these are still going to be the same. Regardless of whether I start with pure water or whether I've got, say, salt water, when I boil the water is still going to end up in the gas phase in the same state. So I'm going to have the same entropy here. The same is true of the solid, which may seem a little less intuitive at first because you've got that salt present, but it turns out that for the most part when water freezes, the solute doesn't freeze as part of the crystal, so we end up just freezing the water by itself and concentrating the solute back down. So now let's look at our various changes in entropy for these processes. Okay, so let's write down our different processes. So let's have our water boiling, and so we'll start with our water liquid goes to water gas. Okay, so I'm going to draw in the delta S for these processes here. So this will be my delta S for this process, my change in entropy, and again this will be my change in entropy here, even though I'm starting with salt in it. now I'm going to have a different change in entropy since I start with a different entropy for my solution compared to my pure liquid. Okay. We can also look at the other process that we're talking about, which is the freezing process, so we can write that down separately. So let's write down our liquid water goes to solid water. So now we can look at what's delta S for this process here. Okay. And so we have a new delta S in this particular case. Okay. So let's start by looking at the boiling case. So we'll color code this here in blue for our boiling case. If this process is going to be at equilibrium, right, so the point at which I go from liquid to vapor readily is the point at which these are in equilibrium. So these are my phase equilibrium line. So when I'm on the phase equilibrium line, then I know that delta G is equal to 0. So my liquid and my gas are at equilibrium. Okay. So what I want to now look at is the Gibbs free energy equation, where I can say the Gibbs free energy is equal to delta H minus T delta S. And now we've assigned that delta G is going to be equal to 0. So now we've got 0 equals delta H minus T delta S. And I'm just going to solve that and say delta H is equal to T delta S in this particular case. Now, let's assume that when we've got the process on the left here, where we're going from pure liquid to gas, or from solution to gas, that delta H is going to be the same here. Okay, so if we assume that this is the same, so let's hold this constant. Okay. And let's see what the effect of having a different delta S is going to be. So I'm going to change this T to just TB to remind me. This is the boiling point, and that's because I said I'm at equilibrium, so I'll be at equilibrium at the boiling point. And so now I've got delta H equals the boiling point times delta S. So now let's look here. Here we've got a larger delta S, and here we've got a smaller delta S. So in the case where we have dissolved something, right, then we are going to decrease delta S. Okay? So as delta S decreases for our system that has a solute in it, then I'm going to have an increase in the boiling point. So that's what we saw here. We have a boiling point elevation. Okay? So I have a smaller change in entropy, and therefore I'm going to have to go to a higher temperature in order to make up for that, since delta H is a constant. We can make a similar argument here when we look at freezing point. So here in this case, the change in entropy is actually unfavorable, so we have a decrease in entropy, and now we're going to have an even bigger unfavorable change in the entropy. So let's look at the same kind of thing. So if this process is in equilibrium, so if we're at the freezing or melting point, then we can say delta G is equal to 0. And again, we'll have the same kind of thing, where we'll have delta H will be equal to T delta S when we're at the freezing or melting point. So I'll label this TF. We often call that TM for the melting point, but the freezing point and the melting point are the same. And since we often call it freezing point depression, I'll call it TF. And so when we then look at our analysis here, in the case where we have the solution, we're going to have a larger value for delta S, and so that means we're going to have a smaller value for the freezing temperature. So we're going to have freezing point depression. So we can make an entropic argument here numerically using the Gibbs free energy equation, assuming that we're holding the enthalpy constant. Okay. So that's the entropic explanation, or one way to look at the entropic explanation for these colligative properties.